Number 10. The mountain that sent smoke signals for 2 years before the valley below stopped watching. In the summer of 1985, the town of Armero sat in the Tolima department of Colombia, nestled comfortably in a river valley that had been home to coffee growers, farmers, and market traders for generations. The town had grown from modest colonial roots into a functional, populated community of somewhere between 20 and 25,000 people. The Lagunillas River ran near its edge. The fields were productive. The streets were ordinary in all the ways that make people feel safe. And rising behind everything, visible on clear days from the town square, was the Nevado del Ruiz volcano, an ice-capped peak sitting at roughly 5,000 meters above sea level. It had been quiet for more than a century. People had largely stopped thinking about it as a threat, but the mountain had been sending signals since 1984. Minor seismic tremors had begun to register beneath the volcano. Steam and sulfur emissions increased through the following year. Colombian geological authorities were aware of the activity. Scientists from the Colombian Geological Survey and visiting international researchers had been monitoring the situation and growing genuinely alarmed. By September of 1985, a preliminary hazard assessment map had been drafted and distributed to local authorities. That map showed Armero sitting directly within a high-risk lahar zone. A lahar is not lava. It is something, in some respects, more dangerous. When volcanic heat melts glacial ice and snowpack on a summit, the water mixes with volcanic ash and debris and becomes a fast-moving river of superheated mud and rock. It does not glow. It does not telegraph itself with dramatic light. It moves in the dark, through river channels, filling valleys quietly, and then suddenly all at once. The hazard map was received, it was discussed, and then, at various levels of administration, it was not acted upon with the urgency the situation demanded. Some local officials expressed concern about causing economic panic. Armero was not a wealthy town. Its agricultural economy was fragile. The idea of a large-scale evacuation based on what still seemed like a hypothetical risk, a volcano that had not erupted in over a century, was not easily accepted. There were also genuine coordination failures. Colombia, in 1985, did not have a unified national disaster management system capable of forcing a response. The warning infrastructure existed in pieces, but not as a connected whole. On the evening of November 13, 1985, Nevado del Ruiz erupted. The eruption itself was not the largest possible event the volcano could produce, but it did not need to be. The heat from the eruption was sufficient to melt a significant portion of the summit's ice and snow. Within hours, lahars were moving down multiple river valleys simultaneously. The Lagunillas River carried the largest flow directly into Armero. The mud arrived after midnight when most residents were asleep. Eyewitness accounts from survivors describe walls of dark material moving through the streets without warning, burying buildings, vehicles, and people beneath meters of compacted debris. The lahar was estimated to have reached speeds of between 30 and 50 kilometers per hour in some stretches of the valley. Armero was submerged in under 30 minutes. The death toll from the Armero disaster is estimated at approximately 23,000 people. The hazard map that had been drafted 2 months earlier had identified the risk with remarkable accuracy. The evidence was not hidden, not subtle, and not ambiguous. A volcano that had been actively venting for over a year with documented seismic instability produced a hazard assessment that named the specific communities at risk. What failed was not the science. What failed was the chain of decisions between the warning and the action. Survivors have spoken about hearing civil defense radio broadcasts earlier that evening telling residents that the situation was under control and that they should remain calm. Some people who had already begun to evacuate turned around and went home. The disaster produced significant changes in Colombian disaster preparedness law and led to the creation of more formal national-level emergency response structures. The hazard map itself is preserved in disaster research archives as a document that demonstrated both how warnings can function and how they can be neutralized by administrative hesitation. The warning existed, the map existed, the science was sound, and the town no longer exists. The next entry on this list also involves a warning that reached the people with authority to act. The difference is that this one arrived in a letter, in plain language, months before an industrial structure failed and drowned an entire valley. Number 9. The inspector who filed the paperwork that nobody read until the water had already killed everything downstream. The Vajont Dam disaster of October 1963 is one of the most thoroughly documented engineering catastrophes in European history, and it is also one of the most disturbing precisely because the warning was not missing. It was not vague. It was not the product of a single concerned voice that could be dismissed as an outlier. The warning was embedded in the technical and geological record of the dam site itself, generated by the same institutions that had approved the project, and it was clearly communicated to people who had the authority to stop what happened. The Vajont Dam was constructed in the Piave River Valley in northeastern Italy in the Friuli Dolomite region during the late 1950s and early 1960s. When completed, it was among the tallest arch dams in the world, rising over 260 meters. The engineering achievement was genuinely impressive by the standards of the era. The dam was built by SAID, an Italian energy company, under Italian government authorization. The Vajont reservoir behind it would serve hydroelectric generation for the expanding industrial electricity demands of post-war Italian development. The geological problem was present from before the dam was complete. The southern wall of the Vajont Gorge, specifically the slope of Mount Toc, was composed of ancient limestone, layered with clay. The clay layers had a particular orientation that made them potential sliding surfaces. Geologists associated with the project, including Leopold Muller, had identified signs that the slope was slowly moving as early as 1959. In 1960, a smaller landslide of several 100,000 cubic meters fell into the reservoir. This was not a minor incident. It generated a wave. The dam held, but the event was documented and studied. The conclusion reached by project engineers and consultants was not that the dam should be decommissioned, but that the water level in the reservoir could be managed to control slope movement. Over the following years, researchers monitoring the slope, including geologist Giorgio Dal Piaz and members of the Italian National Research Council, produced analyses suggesting that the entire southern slope of Mount Toc was potentially mobile as a single mass. The scale of this mass was estimated in the tens of millions of cubic meters. Several formal reports warned that if this mass entered the reservoir rapidly, the resulting wave would overtop the dam. Letters and reports documenting this concern were filed with SADE and with government authorities. The concern was not theoretical speculation. It was based on direct measurement of slope movement velocities that were increasing. The decision to continue raising the reservoir water level in autumn of 1963 was made despite these documented concerns. On the evening of October 9, 1963, approximately 270 million cubic meters of rock and earth detached from Mount Toc and entered the reservoir in a matter of moments. The landslide was so large and moved so rapidly that it displaced the reservoir water in a wave estimated at over 200 meters in height. That wave overtopped the dam in both directions. The dam itself did not break. This detail is both technically remarkable and profoundly terrible because it means the structure held while the water it had stored annihilated the valley below. The flood wave hit the town of Longarone within minutes. It also struck the villages of Pirago, Rivalta, Villanova, and Faye. Nearly 2,000 people died. The dam still stands. The scar on Mount Toc is still visible. The reservoir behind the dam is now permanently filled with landslide debris. What the disaster produced was a series of criminal trials in Italy that lasted for years, examining questions of negligence and institutional responsibility. Multiple individuals associated with SAID were convicted, though sentences were reduced or overturned on appeal through a prolonged legal process that frustrated many survivors. The geological reports, the monitoring data, the internal letters warning about slope instability are all part of the court record. They are preserved. The warning did not disappear. It was generated, filed, read, and ultimately set aside in favor of continued operation. What makes the Vajont disaster specifically relevant to this list is not simply that warnings were ignored, it is that the warning came from the project's own scientific apparatus. The people who were supposed to evaluate the safety of the dam were the ones producing the evidence that the dam's operation was dangerous. The conflict of interest between what the evidence said and what the project required was resolved in favor of the project until the mountain made that resolution permanent. 2,000 kilometers away from the Vajont Valley and 60 years earlier, another warning arrived from the Earth itself, this time through the behavior of water wells, the sudden absence of local animals, and a series of minor tremors that residents reported but authorities characterized as unremarkable. Number 8. The town that watched the ground crack open for days and assumed the worst was already over. The 1908 Messina earthquake struck in the early morning hours of December 28th, a moment when the vast majority of the population of Messina, Sicily, and Reggio Calabria, directly across the strait on the Italian mainland, were still asleep inside their homes. The earthquake is estimated by modern seismological analysis at a magnitude of approximately 7.1. Though some assessments place it slightly higher, it remains one of the deadliest earthquakes in recorded European history. Estimates of total deaths range widely from around 75,000 at conservative counts to over 200,000 in higher estimates, with the uncertainty resulting from the near-total destruction of both cities and the lack of reliable pre-event census data for the affected districts. What makes this entry relevant is what happened in the weeks and days before December 28th. In late November and through December 1908, residents of Messina and surrounding areas had been reporting a series of small tremors. Ground cracking had been observed in some areas. Water in certain wells had reportedly changed in level or in turbidity. Some residents described animals, particularly dogs and livestock, behaving in ways they found unusual. These accounts come primarily from survivor testimonies collected after the disaster and must be treated carefully since post-event memory has a tendency to retroactively assign significance to details that might otherwise be unremarkable. Nevertheless, minor seismic activity in the weeks before a major event in a seismically active zone is not implausible. The Strait of Messina sits along a tectonically complex zone where the African and Eurasian plates interact through a system of faults, including the Southern Apennines fault system. The more systematic warning, however, came not from nature but from human observation. There is documented evidence that at least one individual, a seismologist associated with Italian geological observation, had raised concerns about the seismic risk of Messina before 1908, though the institutional capacity to respond was limited, and the scientific tools for specific earthquake prediction did not yet exist in any reliable form in that era. Broader warnings about the catastrophic vulnerability of Messina as a built environment were available in principle to anyone who understood how the city was constructed. Messina in 1908 was largely a city of unreinforced masonry buildings, many of them multiple stories, built on alluvial deposits near the coastline. The combination of loose soil, shallow water table, and heavy masonry construction was understood by engineers of the period to amplify seismic shaking. Following an 1783 earthquake that had devastated the Calabrian region, there had been some discussion of building codes and construction standards, but these discussions did not produce durable regulatory change. When the earthquake struck at 5:20 in the morning, the shaking lasted approximately 30 seconds. That duration was enough. Buildings across both cities collapsed with a speed and totality that left little space for survival. Fires broke out. A tsunami generated by the seabed displacement reached the coastline within minutes, pulling back the sea first, which caused some curious survivors to walk toward the water, and then driving it forward in waves that inundated the lower districts already buried in rubble. The response from rescue authorities was delayed by the scale of the destruction and by communication failures. Russian and British naval vessels in the strait responded before Italian military units had fully organized, a detail that generated political embarrassment and prompted subsequent reforms to Italian civil emergency response. The structural vulnerability of Messina was not a secret. The city's exposure to seismic risk was embedded in the historical record of the region. What was absent was the political and institutional will to impose building standards that would have made the city's thousands of masonry structures significantly more survivable. The warning, in this case, was less a specific prediction, and more a continuous ambient reality that was managed by collective agreement not to act on it. The next warning was written down, transmitted to the right people, and then found, 30 years later, exactly where it had been filed. Number 7. The dam that a government engineer said would fail, in writing, and was ignored until it killed over 2,000 people in a single afternoon. The Johnstown flood of May 31st, 1889, in western Pennsylvania is remembered today primarily as a famous American disaster, a story of Gilded Age negligence that destroyed a working-class city in a single afternoon. But what it actually represents, when examined through its documentary record, is something more specific and more troubling, a warning that was formally raised, formally received, formally noted, and formally set aside by people who had both the knowledge and the power to prevent it. The South Fork Dam had been constructed in the 1840s as part of a Pennsylvania Canal reservoir system. By 1889, it had passed through several ownership phases and now held back a private recreational lake, Lake Conemaugh, maintained for the exclusive use of the South Fork Fishing and Hunting Club, a membership organization of wealthy Pittsburgh industrialists and their guests. The club had purchased the dam and the surrounding land in the late 1870s and had undertaken modifications to the dam structure. These modifications, according to engineers and historians who have examined the documentary record, compromised the dam's integrity. The spillway had been lowered to allow a road to pass over it, reducing the dam's ability to discharge excess water rapidly. The discharge pipes that had originally allowed controlled release of reservoir water had been removed. The fish screens added to prevent club fish from escaping over the spillway reduced the effective opening area during high water events. The warnings began well before 1889. Engineers who examined the South Fork Dam in the decade prior to the flood raised concerns about its condition. Daniel Johnson Morrell, a Johnstown businessman and former owner of the local Cambria Ironworks, had sent an engineer named John Fulton to inspect the dam in 1880. Fulton's report was detailed and direct. He identified specific structural deficiencies and stated his belief that the dam was in a condition that made it potentially dangerous. Morrell transmitted these concerns to the South Fork Club. The club's response was to assure him that maintenance was ongoing. The issue was not pursued further through any regulatory or legal mechanism, partly because the state of Pennsylvania in 1880 did not have a dam safety inspection authority. There was no governmental body with the mandate to compel a private dam owner to repair or decommission a structure that engineers had flagged as dangerous. On May 31, 1889, following days of exceptionally heavy rainfall that filled Lake Conemaugh beyond its capacity, the South Fork Dam failed completely. The release of 20 million tons of water down the Conemaugh Valley toward Johnstown took roughly an hour to reach the city. Telegraph operators along the valley attempted to warn downstream communities, but the message system was incomplete, and in some areas, the warnings were not received in time, or were received and not believed because the dam had held through previous high water periods, and locals had grown accustomed to treating warnings about it as unnecessary alarmism. One telegraph operator at the South Fork station sent repeated messages warning that the dam was about to fail and that Johnstown should evacuate. Some residents did move to higher ground. Many did not. When the flood hit Johnstown, it carried not just water, but an enormous debris mass of timber, rail cars, houses, and machinery that had been stripped from everything the water encountered on its way down the valley. At a rail viaduct on the edge of the city, this debris mass accumulated and caught fire, trapping people who had survived the initial flood wave but were now immobilized in the wreckage. Over 2,200 people died. In the aftermath, legal action against the South Fork Club was attempted, but ultimately unsuccessful. The courts found that the flood constituted an act of God rather than a product of actionable negligence, a legal determination that frustrated survivors and shaped subsequent American tort law discussions about liability for infrastructure failures. The Fulton Report still exists. The warning was not ambiguous. The mechanism of failure was identified correctly. The modifications that compromised the dam were documented. What protected the South Fork Club from consequence was not the absence of evidence, but the absence of any legal and regulatory framework that could have converted evidence into obligation. The catastrophe waiting in our next entry was not about infrastructure. It was about the air itself, and the warning came from dead animals. Number 6. The valley where livestock began dying from invisible causes, and scientists raised alarms that officials called exaggerated for 2 decades. Lake Nyos sits in the northwest region of Cameroon, a crater lake formed in the caldera of a dormant volcanic structure. On the night of August 21, 1986, a massive and sudden release of carbon dioxide gas from the lake killed an estimated 1,700 to 1,800 people in the surrounding villages, along with thousands of livestock. The cloud of gas, which is heavier than air and therefore hugs the ground, rolled down the hillsides from the lake and into the low valleys where the villages of Nios, Kam, Cha, and Subum were located. People who encountered it lost consciousness within seconds and died within minutes. The gas left no visible trace. Many victims were found in positions that suggested they had simply fallen asleep where they were. The catastrophe was not preceded by any visible physical warning that night, but the events at Lake Nyos in 1986 were not completely without historical precedent or prior signal. 2 years earlier, in 1984, a similar but smaller release of gas from nearby Lake Monaun had killed approximately 37 people. That event attracted scientific investigation, and researchers including French and American geologists working in Cameroon in the mid-1980s had begun to understand the phenomenon of limnic eruption, the term for the sudden overturn and degassing of a carbon dioxide-saturated deep lake. The science being developed in the wake of the Monaun event was directly applicable to Lake Nyos, which sits in the same geological region and shares the same fundamental characteristics. A crater lake in volcanic terrain, fed by carbon dioxide seeping from magmatic sources below, capable of becoming supersaturated with dissolved gas under the right temperature and pressure conditions. The interval between the Monaun event in August 1984 and the Nyos catastrophe in August 1986 was exactly 2 years. During that time, researchers had published findings and communicated concerns about the broader risk presented by other crater lakes in the region, including Lake Nyos. The challenge was not purely one of ignored warnings at the local level. The affected communities were rural, with limited access to government infrastructure. Cameroon in the mid-1980s was not in a position to rapidly deploy monitoring equipment to a remote volcanic lake based on preliminary scientific findings. There were also genuine limitations in the scientific understanding of limnic eruptions at the time, since the phenomenon had not been widely studied and the mechanisms driving the supersaturation were still being characterized. What the Lake Nyos disaster revealed was a category of natural hazard that had existed largely outside the formal framework of disaster risk management. Volcanic lakes capable of catastrophic CO2 release were present in several locations globally, and the identification of Lake Nyos as one of those sites had begun before 1986, but the institutional capacity to act on that identification, to monitor the lake, warn communities, and develop mitigation strategies was not in place. In the decades since 1986, degassing pipes have been installed in Lake Nyos to slowly release carbon dioxide in controlled amounts, reducing the accumulation risk. Similar systems have been installed or proposed for other high-risk lakes in the region. The technology for preventing a recurrence exists. The investment came after the deaths, not before. There is a particular quality to this warning that distinguishes it from most others on this list. The warning was not ignored by powerful institutions protecting economic interests. It was not buried in administrative paperwork. It was acted on by the scientific community as quickly as the state of the field allowed. The failure here was structural, a gap between the pace of scientific understanding and the pace of institutional response, in a region with limited resources to bridge that gap. Nearly 2,000 people lived in that gap. The next warning was far older, far more specific, and delivered not by instruments, but by the behavior of the sea itself on a single day in history. Number 5. The harbor that emptied before the wave, and the people who walked down to look at the exposed seabed. The story of the Boxing Day tsunami of December 26, 2004 is among the most documented natural disasters of the 21st century, but embedded within it is a specific and painful warning story that takes place not in the waters of the Indian Ocean, but on the beaches of southern Thailand, on the island of Simulu, off the coast of Sumatra, and in the operations room of a Pacific Ocean Tsunami Warning Center in Hawaii, in the moments after the magnitude 9.1 undersea earthquake struck the Sunda Trench off the northwestern coast of Sumatra at approximately 7:58 in the morning local time. The sea around the epicenter region underwent a characteristic behavior that has been recognized as a precursor to a tsunami for centuries. The water along the coastline receded dramatically and rapidly, pulling back hundreds of meters from the normal shoreline and exposing the seabed, reef structures, and stranded fish. This event, the drawback, is caused by the leading trough of the tsunami wave preceding the crest. It is the sea inhaling before it strikes. On beaches in southern Thailand and Sri Lanka and parts of India's eastern coast and the Andaman Islands, people who witnessed the drawback responded with curiosity. They walked out onto the suddenly exposed seabed. They collected fish. Children played. Photographs and video footage taken in the minutes before the wave arrived show people standing on normally submerged ground, looking out at the retreating water with puzzlement rather than fear. The knowledge that a rapid and dramatic sea withdrawal precedes a major tsunami was not universally distributed in the communities facing the Indian Ocean in 2004. There was no Indian Ocean tsunami warning system in operation on that morning. The Pacific Tsunami Warning Center, based in Hawaii, had detected the earthquake within minutes and understood its potential to generate a major tsunami, but they had no established communication protocol with Indian Ocean coastal governments, no contact list, no pre-existing relationship that would have allowed them to transmit a warning to the right authorities fast enough to make a difference. The contrast with Simuliu Island is important and has been widely documented. Simuliu sits just 60 kilometers from the earthquake epicenter, close enough that the seismic shaking was severe and the tsunami arrival time was extremely short, yet the island lost only a small number of people relative to its population, despite being almost directly in the path of the most powerful tsunami waves. The reason, documented by researchers who studied the island's response after 2004, was oral tradition. Simuliu had experienced a devastating local tsunami in 1907, and the collective memory of that event had been maintained across generations, through stories specifically describing the behavior of the sea before the wave. Islanders who felt the earthquake and saw the sea withdraw immediately fled inland. The knowledge was old, specific, and correct. The formal warning apparatus that failed on December 26, 2004 was not the result of a secret. The Indian Ocean lacked a warning system because no comprehensive catastrophic tsunami had struck the region in the era of modern monitoring infrastructure. The Pacific system existed because the Pacific had generated catastrophic tsunamis in the 20th century that drove its creation. The risk was known to researchers and to international geological bodies. Proposals for an Indian Ocean monitoring network had been discussed in scientific circles prior to 2004, but the sustained political and financial commitment required to build such a system had not materialized. It materialized within 2 years of the disaster, after approximately 227,000 people were dead. The warning that failed in this case was not a single document or a single voice. It was a category of institutional preparedness that had never been built for a region that had not experienced a catastrophic tsunami in living memory. History had provided the precedent. The mechanism was understood. The building of the system was not prioritized until the system's absence had already defined its cost. The next entry takes us to a city in ancient times where the warning was not a scientific measurement, but a physical transformation of the landscape so dramatic that it permanently reshaped the surrounding geography for miles in every direction, and still people did not leave. Number 4. The ancient city that kept rebuilding itself inside a volcano's caldera because nobody alive remembered what the mountain had done the last time. The Roman city of Pompeii sits approximately 10 kilometers southeast of Vesuvius in the Campanian plain of southern Italy. Its destruction on August 24th of 79 CE is perhaps the most thoroughly studied volcanic catastrophe in Western historical memory, partially because it produced a vivid literary account from Pliny the Younger, whose uncle Pliny the Elder died during the eruption while attempting to rescue people by boat from the bay. The letters Pliny the Younger wrote to the historian Tacitus decades later remain the closest thing to a contemporary eyewitness account of the event. But the story most relevant to this list is not the story of the eruption. It is the story of what happened 17 years before it. In 62 CE, a severe earthquake struck the Campania region with particular violence. The cities of Pompeii and Herculaneum both suffered extensive damage. Buildings collapsed. The water infrastructure of Pompeii was severely disrupted. Statues fell. The temple of Jupiter in the Forum was badly damaged. This was not a minor tremor. The earthquake was significant enough that the Roman philosopher Seneca wrote about it in his Naturales Questiones, specifically discussing the Campanian earthquake as an example of the power of subterranean forces. Archaeological evidence from Pompeii confirms that at the time of the eruption in 79 CE, 17 years after the earthquake, the city was still in the process of being repaired. Scaffolding and building materials were present at multiple sites. The Temple of Jupiter had not been fully restored. The water system, which fed the city's public fountains, baths, and private houses through a network of lead pipes and distribution towers, was apparently still showing disruptions, with evidence that some water pressure anomalies were present in the period before the eruption. The 62 CE earthquake was, in hindsight, a precursor event. Seismologists studying volcanic systems have documented that earthquake swarms and elevated seismic activity around volcanic structures frequently precede eruptive events by years or even decades, as magma movement at depth creates stress in the overlying crust. The Romans of 62 CE had no framework for understanding this relationship. Volcanology as a science did not exist. Vesuvius itself had not produced a major eruption in centuries, possibly over 1,000 years before 79 CE, and there is no documented collective memory in Pompeii of the mountain as a source of destructive volcanic activity. The mountain slopes were heavily cultivated with vineyards and farms, valued for the exceptional fertility of volcanic soil. The mountain was part of the landscape, not a perceived threat. In the summer of 79 CE, in the weeks and days before the eruption, there were additional warning signals. Small earthquakes had been occurring with increasing frequency. Springs and wells in the area reportedly dried up or became disrupted. The behavior of the local water table suggests that underground hydraulic changes were occurring as the magmatic system pressurized. On the morning of August 24th, the eruption began with a series of major explosions that sent a column of gas and pyroclastic material approximately 20 to 30 kilometers into the atmosphere. The column collapsed multiple times over the following 18 hours, sending pyroclastic density currents, fast-moving flows of superheated gas and volcanic debris across the surrounding landscape. Pompeii was buried primarily by ashfall and then by pyroclastic surges. Herculaneum, closer to the volcano, was engulfed by pyroclastic flows of a higher density and temperature. The eruption killed thousands of people, with death toll estimates varying considerably since the entire population is not known. The casts of human bodies preserved in the ash layers at Pompeii formed when the cavities left by decomposed remains were filled with plaster during archaeological excavations beginning in the 19th century show individuals in positions of cover, of flight, and of collapse. Some show people who appear to have been sheltering in place, perhaps believing the worst was over when the column briefly stabilized. The warning embedded in the 62 CE earthquake was real and documentable. The response was to rebuild, not to relocate. The mechanism that kept people in place was not ignorance alone, but the entire social, economic, and cultural logic of Roman urbanism. A city was a permanent investment. Its temples, its forum, its baths, its market infrastructure, its water supply all represented generations of accumulated civic expenditure. You did not abandon a city, you repaired it. The decisions that would have been necessary to prevent the deaths of 79 CE would have required the Romans to do something they had no scientific or cultural framework for doing, to recognize that the earthquake of 62 CE and the volcanic system overhead were part of the same underlying danger. That recognition was not available to them. What they had instead was the mountain, visible, quiet, and covered with vines, and 17 more years of ordinary life. Number 3. The government that received 3 formal reports warning of a specific design flaw in a specific nuclear reactor, and chose not to act on any of them before it became the worst nuclear disaster in history. The Chernobyl nuclear disaster of April 26, 1986, has been extensively studied, documented, and debated over the 4 decades since Unit 4 of the Chernobyl nuclear power plant in the Ukrainian Soviet Socialist Republic exploded during a safety test in the early morning hours. The physical mechanism of the disaster, the runaway reactor, the steam explosion, the graphite fire, the release of radionuclides across large areas of Europe is well documented. What is less consistently discussed in popular accounts is the paper trail, the warning trail, the sequence of technical communications that had identified the fundamental design flaw in the RBMK reactor type before April 1986 within Soviet nuclear engineering circles, and documents that were classified, minimized, and functionally suppressed within the Soviet bureaucratic system. The RBMK reactor, which stands for the Russian language abbreviation for a high-power channel type reactor, had a characteristic known as a positive void coefficient, specifically a positive steam void coefficient, under certain operating conditions. In practical terms, this meant that under specific circumstances, if reactor power dropped to a critically low level and steam bubbles formed in the cooling water, the nuclear reaction could accelerate rather than diminish. This was the opposite of the behavior that made other reactor designs inherently self-stabilizing. It was a design property that made the RBMK dangerous under precisely the kind of unstable low-power condition that the April 1986 safety test was attempting to evaluate. Soviet nuclear engineers knew about this property. The question that historians and nuclear safety researchers have worked to answer is not whether the property was known, but who knew it, what they said about it, and what was done with what they said. Evidence reviewed in post-Soviet era disclosures indicates that concerns about RBMK reactor instability at low power had been raised in internal Soviet nuclear engineering and physics reports prior to 1986. Anatoly Dyatlov, the senior engineer who directed the fateful safety test, has been scrutinized extensively, but the broader institutional context is equally significant. The Soviet Ministry of Medium Machine Building and the organizations responsible for RBMK reactor safety oversight had received technical analyses that identified the positive void coefficient and its implications. These analyses did not produce mandatory operational changes, mandatory operator training updates about the specific risk, or modifications to the reactor control systems before the accident. Part of the explanation lies in the structure of Soviet scientific and industrial secrecy. Safety incidents at Soviet nuclear facilities were classified. When other RBMK reactors experienced instability events at low power prior to 1986, the information about those events was not systematically shared with the broader community of engineers operating RBMK plants. The lessons from one incident were not translated into mandatory procedural changes across all facilities. The system was organized around the presumption of reliability rather than the communication of failure. Admitting that a reactor design had a potentially catastrophic flaw was not a statement that could move freely through Soviet bureaucratic culture. It was a statement with career consequences. The test that was being conducted on the night of April 25th and the early morning of April 26th was actually a safety test, meant to evaluate whether the turbines of the reactor could generate enough electricity during a coast down to power the emergency cooling systems in the interval between a reactor shutdown and diesel backup generator activation. The test had been attempted at Chernobyl before and had not been completed successfully. The version conducted in 1986 was being run under conditions that the reactor's own operating instructions prohibited, with power levels far below the safe operational range, with safety systems manually bypassed to allow the test to continue. The operators were not informed, at the level they needed to be, about what the reactor's behavior would be at those power levels. The training materials did not adequately address the positive void coefficient risk at low power. When reactor power surged during the test at approximately 1:23 in the morning, the attempt to insert control rods failed to arrest the reaction in time. The rods themselves had a design flaw that caused a brief power spike as they entered the core. The reactor output spiked to many times its design capacity in a fraction of a second. The resulting explosion was not a nuclear detonation, but a steam explosion, followed by a second explosion, possibly involving hydrogen, that destroyed the reactor building and blew the reactor lid off the top of the core. The graphite moderator caught fire. The open core burned for days, releasing an enormous plume of radioactive material that spread across Ukraine, Belarus, Scandinavia, and much of Europe, contaminating agricultural land and water supplies across hundreds of thousands of square kilometers. The Soviet government's initial response was to attempt to manage information rather than manage the disaster. Evacuations of Pripyat, the city built to house Chernobyl workers, were delayed by approximately 36 hours, while officials debated how to characterize the event. Workers involved in the initial response, including firefighters who were not told the nature of the radiation hazard they were entering, received lethal doses. The international community began detecting elevated radiation levels from monitoring stations in Sweden before the Soviet Union acknowledged that anything serious had happened. The warning existed in the technical literature. The design flaw was documented. The danger under specific operating conditions was known. What the Soviet system could not do was allow that danger to be communicated in a way that produced the structural changes, the redesigned control systems, the comprehensive operator retraining, the mandatory operational restrictions that would have changed the outcome of April 26, 1986. The final two entries on this list involve warnings at a scale that did not apply to a single structure, a single city, or a single technology. They applied to entire ecosystems and entire populations, and in both cases, the people who needed to act most urgently were also the people with the least structural interest in doing so. Number 2. The scientist who handed every major government on Earth a report predicting the exact catastrophe that was coming, and was thanked for her work and sent home. Rosalind Franklin, James Hansen, Roger Revelle, Eunice Newton Foote. The history of climate science is populated by researchers who established with accumulating precision what increasing atmospheric carbon dioxide concentrations would do to global temperatures, to sea levels, to storm intensities, to drought patterns, and to agricultural viability. But the specific warning event that belongs in this slot is not the history of climate science in general. It belongs to a more specific and more documentable moment. The 1988 United States congressional testimony of James Hansen, director of NASA's Goddard Institute for Space Studies. On June 23, 1988, during a heatwave in Washington, D.C., Hansen testified before the Senate Energy and Natural Resources Committee and stated with what he characterized as high confidence that the warming trend then being observed in global temperature records was not a natural fluctuation. It was the enhanced greenhouse effect. The cause was human emissions of carbon dioxide and other greenhouse gases. The consequences, he testified, would include continued warming, rising sea levels, more intense drought events, and more extreme weather. He had supporting data. His models had been tested. His institution had decades of observational records behind the analysis. The testimony was covered in the media. It was entered into the congressional record. It was discussed at the policy level. And the prior scientific foundation for Hansen's 1988 statements was considerably older. Eunice Newton Foote had demonstrated in 1856 that CO2 absorbed more solar radiation than other gases. Svante Arrhenius had calculated in 1896 that doubling atmospheric CO2 concentrations would produce significant warming of the Earth's surface. Charles David Keeling had been measuring the continuous rise of CO2 at Mauna Loa since 1958. Producing what became known as the Keeling curve, the most iconic record in atmospheric science, showing the relentless annual increase of CO2 in the atmosphere, year after year, without exception. By 1988, the science was not new, it was not preliminary, it was not based on computer models alone, it was based on physics, on direct atmospheric measurement, on deep paleoclimate records from ice cores and sediment layers that showed the historical relationship between CO2 concentrations and surface temperatures going back hundreds of thousands of years. The 1988 testimony placed that entire scientific edifice directly in front of legislators whose decisions about energy policy, fuel standards, subsidies, and international agreements would determine whether industrial societies began transitioning away from fossil fuel dependence in time to limit the most severe consequences. What followed 1988 was not inaction in every dimension. International scientific panels were organized. The Intergovernmental Panel on Climate Change was established in 1988. International framework agreements on climate were negotiated through the 1990s, but the fundamental trajectory of fossil fuel consumption, of coal plant construction, of oil extraction and refinery capacity did not reverse. It continued to increase globally. The atmospheric CO2 concentration that stood at approximately 350 parts per million in 1988 climbed past 400 parts per million by 2013 and has continued rising. The consequences Hansen described in 1988, the warming, the sea level rise, the drought intensification, the extreme weather escalation, have materialized in the observational record with a correlation to the projections that is difficult to characterize as coincidence. The warning in this case was not missed because the evidence was weak or the mechanism unclear. The warning was given precisely, publicly, backed by the most rigorous scientific foundation that any warning on this list can claim. The failure was not epistemic, it was structural. The economic and political systems organized around fossil fuel extraction were not capable of responding to the warning with the urgency the evidence demanded because the cost of that response would fall on interests that were capable of lobbying, funding alternative narratives, and delaying binding action for decades. Hansen's 1988 testimony came with a precise and specific framework for what would happen if the warning went unheeded. The record of what happened next is not hidden. It is measured, documented, published, and visible in the temperature anomaly data of every year since he spoke. Number 1. The ships that radioed the warnings and the one ship that chose speed over the ice it already knew was there. Of every entry in this list, the Titanic disaster of April 14th to 15th, 1912, in the North Atlantic Ocean occupies a peculiar place in the landscape of ignored warnings. It is by far the most culturally documented. It has generated more books, films, inquiries, and public commentary than virtually any other single maritime disaster in history. It is in some respects almost impossible to discuss, because the story seems so thoroughly known, and yet the specific warning chain leading up to the collision with the iceberg that sank the ship remains one of the most clinically precise and sobering cases of a warning received, acknowledged, and then set aside in the history of catastrophic maritime navigation. The Titanic departed Southampton on April 10, 1912. It was the maiden voyage of the White Star Line's largest and most expensive vessel, over 269 meters in length, with a gross tonnage that made it the largest ship then afloat. The ship carried a complement of approximately 2,224 people across all passenger classes and crew. The voyage attracted enormous public attention because of the ship's scale, its technological appointments, and the social prominence of some of its first-class passengers. In the days before the collision, the Titanic's wireless room had received multiple ice warnings from other ships operating in the same transatlantic shipping lanes. These messages were arriving via the Marconi wireless system, the communication technology that was still relatively new in 1912, and operated partly as a commercial service for passenger telegrams, and partly as a navigational communication tool. On the morning of April 14th, the day the ship struck the iceberg, at least 5 separate ice warning messages were received from other vessels in the area. These messages described large icebergs, field ice, and growlers, the term for smaller ice fragments, directly in the path of shipping lanes the Titanic was using. One of the most significant warnings came from the Masaba, sent in the afternoon of April 14th, which described a large field of ice directly ahead of the Titanic's course. That message was received by the wireless room, but was apparently never delivered to the bridge. The SS Californian, a vessel that had stopped for the night because its captain, Stanley Lord, determined the ice conditions were too dangerous to proceed, transmitted a warning to nearby ships that evening. The Californian's wireless operator, Cyril Evans, attempted to contact the Titanic to warn about heavy ice. The Titanic's wireless operator, Jack Phillips, was overwhelmed with a backlog of passenger telegrams and told Evans to stop blocking his signal. Evans shut down his wireless equipment and went to sleep shortly before midnight. The Titanic struck the iceberg at 11:40 that evening. Captain Edward Smith had been informed of the ice warnings received earlier in the day. The ship's speed on the night of April 14th, approximately 22 knots, was not significantly reduced despite the known presence of ice in the area. The conditions that night, a calm sea, no swell, no moon, no wind, were actually the worst possible conditions for iceberg detection by visual lookout, because the absence of breaking waves at the base of an iceberg eliminated the white water that normally helps spotters identify ice at night. The lookouts in the crow's nest had been informed of the ice risk and were watching carefully, but their binoculars had been locked away in a cabinet whose key had been misplaced before departure. A detail documented in the British Board of Trade inquiry that followed the disaster. The Titanic struck the iceberg at an angle that opened a series of hull compartments below the waterline, along a length of the ship that exceeded the design tolerance of the watertight bulkhead system. The ship was designed to remain afloat, with any 4 of its forward compartments flooded. The iceberg contact compromised 5. The ship took approximately 2 hours and 40 minutes to sink. It carried lifeboats with capacity for approximately 1,178 people from a complement of 2,224. The lifeboat provision met the legal requirements of the British Board of Trade's regulations, which had not been updated to reflect the increasing size of passenger vessels. The shortfall between lifeboat capacity and total passengers was not a secret. It was a known feature of the ship's design that had been discussed before departure, and accepted on the grounds that the ship's safety features were understood to reduce the likelihood of needing full lifeboat capacity. What makes the Titanic the first entry on this list, rather than simply another entry, is the compounding architecture of the warnings. There was not one warning. There were multiple ice warnings over multiple hours from multiple ships. There was a navigational decision to maintain high speed through a region the bridge crew knew contained substantial ice. There was a structural lifeboat deficiency that was not hidden but legally accepted. There was a wireless communication failure in the final hours that kept the most urgent ice report from reaching the officers on watch. There was a technology gap in the lookout's equipment, and there was the broader cultural context of the maiden voyage, the commercial pressure, the competitive interest in demonstrating the ship's speed and capability, the social atmosphere aboard a vessel that the contemporary press had described as the ultimate expression of maritime technology. Each of these elements individually was survivable. Together, they produced a situation where the warning arrived in multiple forms, was received at multiple points in the chain of command, and was nonetheless not converted into the navigational caution that would have mattered. The Titanic's collision was not inevitable. It required, simultaneously, the presence of the ice, the decision to maintain speed, the failure to deliver the Masaba warning, the absence of binoculars in the crow's nest, and the 2 hours and 40 minutes that followed, during which the gap between how many people the ship could carry and how many it could save produced 1,500 deaths in the North Atlantic. The British Board of Trade inquiry and the American Senate inquiry that followed the disaster both examined the warning chain. The transcripts run to thousands of pages. The warnings are there. The decisions are there. The gaps are there. The record preserves it all with a completeness that few disasters in this list can match. What remains difficult to fully account for, across every entry in this list, is not the absence of knowledge. It is the distance between knowing and doing. The geologists who mapped the Lahar Zone at Armero, the engineers who documented the instability at Vajont, the inspector who wrote the report about the South Fork Dam, the seismologists who understood what Messina's buildings would do under seismic stress, the researchers who began to understand limnic eruptions before Lake Nyos, the physicists who documented the RBMK's instability, the atmospheric scientists who built the observational record of climate change across an entire century, and the wireless operators and officers on the bridge of the Titanic who received the ice warnings and kept moving. Every one of them knew something that mattered. Every one of them operated inside a system that, for reasons of economics, politics, bureaucracy, confidence, or the ordinary human difficulty of acting on danger that has not yet arrived, could not convert what was known into what was done. The warnings did not fail because they were wrong. They failed because being right was never enough on its own. Think about the warning on this list that troubles you most, the one where the failure seems least forgivable, and put the number in the comments. Every entry here has a different reason the knowledge did not become action, and those reasons have not stopped applying. If this kind of documented dark history is what you want more of, subscribe to the Catastrophe Ledger.